Okay, this will be a short lecture. So this will be short because I'm going to do the first part of the lecture because I have a second part that was pre-recorded. So I'm just going to get us to that part, and then I'll send out the second part for you guys later on. So we're going to start looking at isomerism, which we've met already to some extent. We're just going to kind of put it together today. So isomerism then is the existence of different compounds with the same chemical formula. Okay? And we've already seen that we can divide isomerism, or divide isomers, into different types, right? We have constitutional isomers, and we could divide those, we could look at those, for example, as if we look at ethanol versus dimethyl ether. That's a classic example. Those are constitutional isomers. But we can also have, we've seen geometric isomers. And geometric isomers arise when there is restricted rotation. So for example, I could look at these being the trans and the cis isomers of each other. And that also applies, for example, to, as we've seen, cyclohexanes or cycloalkanes. So this is the cis 1,3-dimethyl species. On the other hand, this would be the trans 1,3-dimethyl species. Right? So that's geometric. We've also seen conformational isomers. So, for example, we could look at that, which is the anti-conformer of butane, versus this, which is the fully eclipsed conformer. Or we can draw those in the Newman projection formulas to look something like this. Right? This is the anti, and this is the fully eclipsed conformer. Oh, shoot, this is butane, so this will be CH3, CH3, same thing here, so CH3 or methyl, and then these are the H's. But we've also seen this arise in the cyclohexanes, for example. So I might look at the methyl cyclohexane, either in this chair form or in that chair form. Yikes. Okay. So this is where the methyl is axial, that's where it's equatorial. And of course, not that we consider it much, but it's also the boat conformer for the species. Okay? It's also the boat conformer for that species. So there are lots of different conformational isomers, or conformers. It turns out that what organic chemists realize is that, and I've just drawn 3 different sets here, but there are lots of other subsets that start emerging. And organic chemists realize, well, this is kind of a runaway train because you're developing 12, 13, 14, 15 different subsets of isomers. So organic chemists got together and decided, well, let's try to pull these together under a few umbrellas and identify really maybe just 1 or maybe just 2 fundamental different types, and then have maybe those types have subtypes that they sort of pair with. To that end, what we came up with is that isomers really fall into 2 very broad classes. And I know you guys can rewind this, so I'm not going to be worried about that part too much. Isomers can be divided into 2 very broad subclasses, which are, let me get a darker color. So isomers can be divided into 2 subclasses, which are constitutional. Seriously? Which are constitutional and then stereoisomers. So all isomers fall into those classes. They're either constitutional, and they differ by connectivity, who's attached to whom. So that's your dimethyl ether versus your ethanol, we just looked at earlier. But stereoisomers differ. Stereoisomers have the same constitution. So in terms of who's connected to whom, they're exactly the same. But they differ in their three-dimensional arrangement of groups. We can further, and so really, if you think about it, well, I've kept a couple here. The cis and trans isomers of the cycloalkanes, the cis and trans isomers of alkenes, the different conformers of butane and ethane and so on, and the cyclohexanes, those have the same connectivities, right, within a set, right? This is 1, 3, that's 1, 3. They have the same connectivity, but their three-dimensional arrangements differ. So that means that my geometric isomers, cis-trans, my conformational isomers, right, whether we're dealing with the axial, the equatorial, the chair, the boat, they are all types of stereoisomers. They've got the same connectivities, but the groups differ in their three-dimensional arrangement. So what do we then, how do we subdivide this set to deal with the explosion of options? And the answer is we will divide our stereoisomers into two broad classes. There are enantiomers, and then there are diastereomers. So we're going to divide our stereoisomers into two types, enantiomers and diastereomers. So what are enantiomers? So enantiomers are mirror image stereoisomers. In other words, they are isomers who are mirror images of each other. We'll explore those in a second. Diastereomers, on the other hand, are non-mirror image stereoisomers. In other words, these are stereoisomers that are not mirror images of each other. And that's probably an easier place to start. So for examples of these might be trans 2-butene and cis 2-butene, right? There's no mirror, right? There's no valid mirror between them. Because clearly I reflect methyl to methyl, vinylic carbon to vinylic carbon. But whereas this methyl is up, that one is down. In a similar fashion, if I'm looking at an anti-conformer, that is not the mirror image of of this conformer. If I'm looking at a staggered, that's not the mirror image of an eclipse. If I'm looking at the chair, the chair is not the mirror image of a boat, or for that matter, if I had a group in an axial position, right? If I had a group in an axial position here, that is not the mirror image of one that has the group in the equatorial position. Right? So these mirror planes, I'm going to put a big X to indicate that there is no mirror plane here. So these are clearly isomers. This is C4H8. They have the same constitution, methyl onto vinylic carbon, methyl, same constitution. But so they're not constitutional isomers. So they must be stereoisomers, and they are, because their three-dimensional arrangements of groups differs. Well, what kind of stereoisomers are they? Are they mirror images of each other? Well, no, they're not mirror images, and therefore these are referred to as diastereomers. So the non-constitutional set of isomers that we've met so far, the geometric isomers, the conformational isomers, those really all fall under the subset of diastereomers, right? So they are non-mirror image stereoisomers. So what exactly then are mirror image stereoisomers? What are enantiomers? And how do they arise? So I'm going to treat this in a very simple way, which really gets to the heart of it. And what we do is play a little game where we look at various species within a set and see what happens to them when we substitute groups. So I'm going to draw a table. And again, as I said, I'm doing this in a simple way. It's a little bit more convoluted than I'm actually doing it, but that's fine. So we're going to start with a species. We're going to ask if it has a mirror image. We're going to ask if it has a mirror plane. And the symbol we use for mirror plane is sigma. So we're going to ask, is there a mirror plane? And we're going to ask, is the object equivalent to the image? So the species we're going to pick are, say, CW4. Excuse me. Let's get CX. So CX4, CX3Y, CX2YZ, and then CXYZA. Okay? So we're going to take, and this is true, and I have it for carbon, but this really is true for any tetrahedral atom. Okay? And what we're going to ask is, if I take CX4, so here's a carbon with 4 same groups, H, Cl, right, anything around it. And I'm going to ask, does this molecule have a mirror image? Now, I'm going to tell you the answer to this question is always yes. Everything has a mirror image. Unless you're a vampire, vampires don't have mirror images. But every molecule has a mirror image. So I can really go ahead and say yes for each of these. That's true. Everything has a mirror image. If you put it in front of a mirror, unless you're the undead, there's a reflection. So here's one molecule, and I'll walk down here. Here's my molecule. Okay? Here is the imaginary mirror, and this is the image behind the mirror. Okay? Oh, there's a column missing here. So object and image. Superposable. And then object equivalent to image. So my CX4 has a mirror image. Does it have a mirror plane? Well, so what's a mirror plane? A mirror plane is a line, well, I'm sorry, it's a plane, it's a surface that bisects an entity so it reflects one half into the other half. So if you look at one of these chairs, right, these chairs have a mirror plane, okay? The mirror plane runs along this axis, dividing this right half into the left half. There is no mirror plane here, okay? So this molecule is a mirror plane. So humans also roughly have a mirror plane that runs down the middle. There's no mirror plane here. If you had those chairs, right, that have the arm that you can lift and write on, well then those don't have a mirror plane either, right? Because if you slid down the middle, if you had a plane in the middle, the chair here, the arm here doesn't reflect on an arm there, okay? So a mirror plane is an internal, because it runs through the object, it's an internal plane, a two-dimensional surface that reflects half, left half or right half into the other, top half, bottom half, whatever, front half, back half. So if I look at this molecule and I ask, does it have a mirror plane? Does it have a sigma? So there are, and when you do more chemistry, there are things called symmetry elements. And one of them is a mirror plane. And the symbol for the mirror plane is sigma. Okay, does it have a sigma? Well, yeah. There is a plane of symmetry running straight down that will cut, let's say it's an H, cut the H in half, reflecting right and the left. Cut this H in half, reflecting right and the left. And straight down the middle, it'll cut through the carbon, but it'll reflect this whole H into that whole H. So there's a mirror plane here. Turns out there's also one here and one here. So it's actually got 3 mirror planes. All I need to know is if it has one, and it has at least one, so this species has a mirror plane. So I'm going to say, yes, it has a mirror plane. I'm going to ask, are the object and the image superposable? And the reason I'm looking at superposability is that superposability is in many ways our test for sameness. If I ask you, is an orange the same thing as an apple? What you do without really thinking about it is you try to superpose them. Do the shapes match? Do the colors match? Do all the profiles match? So our test for sameness is superposability. So is my object and my image, or my object and image the same? And are they equivalent? Are they superposable? Not the same. I've got one on my left and one on my right. But if I move them to the mirror, well then they merge, right? I can have, my H on H, H on H, carbon on carbon, H on H, and so on. So they're superposability, they're superposable. So I'm going to say that they are equivalent species because they match our intuitive test for sameness. So the object and image are superposable, therefore they are equivalent species. What does that mean for us? It means all molecules of CH4 are identical to each other. They're not isomers of each other. All molecules of CCl4 are identical to each other. All molecules of SiOH4 are identical to each other. Okay? There is no isomerism in a CX4 or in anything that is tetrahedral X4. Alright, well, what if we had CX3Y? So let's put a substituent on our carbon. So here is CX3Y. Okay, CX3Y. And I'm going to build the mirror image. And so does CX3Y have a mirror image? Yeah, here it is. Okay. Does it have a mirror plane? Well, yeah. It turns out to have the same 3 as CX4. 1, going straight to the molecule. 2, going through the molecule 3. Okay? I'm going to stop there for a second. So let me fill out this part. It has a mirror plane. It has a sigma. Oh, yeah, it has a sigma. And the question is are the object and the image superposable? Well, let's see. So here we are. I'm going to move the image through the mirror, and white goes on white, blank on blank, blank on blank, carbon on carbon, blank on blank. So we are superposable. We have passed the test for sameness, and therefore the object and the image are the same. In other words, all molecules of methanol, CH3OH, are identical. All CH3Cls are identical. What about CX2YZ? CX2YZ. So here is C. Red ones. So here is CX2. So CX2YZ. And I'm being deliberate in building the mirror image, right? So CX2YZ. So does CX2YZ have a mirror image? Absolutely. Everything does. And I built it. Right? I put it down for the mirror, I built it. Does it have a mirror plane? Well, if I do this straight down the middle, that is a mirror plane. But unlike the 2 predecessors, CXY and CX3Y, CX4 and CX3Y, which had 3 mirror planes, this only has 1. This is no longer a mirror plane, because you reflect the red ball into the black. This is no longer a mirror plane because you reflect the reflect the red ball into the blank. So it only has one mirror plane now, but that's okay. We just need to know if it has any. So it has a mirror plane, and I'm going to ask, are the object and the image superposable? Are they equivalent species? And if I do this to the mirror, well then they don't superpose. I've got white on white, but then my red and my blank as I'm holding them don't match. Not to worry, I'm going to tumble the molecule, because this molecule is that molecule, is this molecule, is that molecule. I'm just going to tumble it and rotate it so that, as it turns out, they do superpose. Red on red, white on white, blank on blank, blank on blank. So it has a mirror plane. It has the mirror plane. It passes the superposability test, and the object and the image are equivalent. So let's go ahead now and build CXYZA. So CXYZ, I'm going to make A, so put some group on. And again, I'm going to be intentional about building the mirror image. All right, so I'm going to put the, and I know everybody's a mirror image, so I'm going to go ahead and build it. So I'm going to put this on. And when I look at it, right, here's my object, here's my image. So does it have a mirror image? Absolutely. Everybody does. So I knew the answer to that one. Does it have a mirror plane? Well, if I hold a molecule, there's no mirror plane here, and I'm going back to the same places because it's tetrahedral. There's no mirror plane here because I reflect blue into blank. There's no mirror plane here because I reflect blue into red. There's no mirror plane here, right, because I reflect red into blank. So this molecule, for the first time in the set, is devoid of sigma. It does not have a mirror plane. We say it is devoid of sigma. Okay. Are the object and the image superposable? Well, I'm going to move them to the mirror, and when I hold it like that, the white and whites match, the blue and the blue match, but the blank and the red don't match. Not to worry, I can tumble it as I did before, and I'll tumble it to get the red and the blanks to match. Yeah, to get the red and the blanks to match. Oh, that was hard. So I can get the red and the blank to match, but now the blue and the whites don't match. And you can do this from now until the cows come home, they will never match. So these two are not superposable. They do not pass the sameness test, and therefore these are different compounds. Right? These are isomers of each other. But how are they isomers? Well, they're different compounds with the same molecular formula, right? C, white, blue, red, blank. They've got the same connectivity, but their spatial orientations of groups differ. So for example, if I hold it this way, you would see from your vantage point with the blue going up and the red coming towards you, white is on your left in this molecule, but it's on the right in this molecule. Blank is on your right in this molecule, blank is on the left in this molecule. So their three-dimensional arrangements are different. These are stereoisomers. Well, what kind of stereoisomers? Well, they're mirror image stereoisomers, and therefore these are enantiomers. So enantiomerism, and again we're doing this from a simple perspective, enantiomerism then arises for the first time when the molecule is devoid of sigma. And so we call these carbons, or any tetrahedral site for that matter, where the groups, so if I have a tetrahedral atom, so I'm going to put carbon, a tetrahedral atom, that has 4 different groups around it. This carbon is special, and it's called a stereocenter. Now in some textbooks, they're called stereogenic centers. Okay? In the old days, they were called chiral centers. That's a really stupid name for them. and most authors have gone away from that, but they're called stereocenters, right, or stereogenic centers, because those are the centers that create this kind of stereoisomerism. So that's the genesis of it, so the stereogenic centers. So a stereocenter is a tetrahedral carbon, tetrahedral site. It could be a nitrogen or an oxygen for that matter, or silicon. So, but the common ones for us, because we're organic chemists, is carbon. A stereocenter is a tetrahedral site that has 4 different groups around it. So I guess the first exercise would be for us to identify which of the sites in a molecule are stereocenters. Right? Which of the sites in a molecule are stereocenters? Okay, so I'm looking for a tetrahedral site that has 4 different groups around it. So let's see who we can rule out. Well, I can rule out this carbon and that carbon because they're linear. Those carbons are sp hybridized, they're linear. To be tetrahedral, you have to be sp3, right? sp2 is trigonal planar, sp is linear. So I can rule out this one, that one, that one, and that one. They're not tetrahedral. My requirements are tetrahedral with 4 different groups around it. X, Y, Z, A. Okay? So if I'm not tetrahedral, I'm out of the game. This carbon is tetrahedral. I haven't drawn it like that, but it is sp3 hybridized. Right? There's no pi bonds on it. And that has on it D, OH, the H is understood here, and then all this graph. So that's 4 different groups on this carbon, which is tetrahedral. That's a stereocenter. By convention, stereocenters are labeled in molecules with an asterisk. What about this one? Well, here I can see the wedge and the dash, right? Which is kind of how these things are set up. But that's kind of smoke and mirrors, because this carbon has 2 H's. Therefore, it doesn't have 4 different groups. So although it's tetrahedral, it doesn't have 4 different groups, and it's not a stereocenter. Well, that carbon is tetrahedral. Right? All the carbons in rings, unless there's a double bond, are tetrahedral. sp2 hybrid, sp3 hybrids anyway. And it has 4 different groups. It's got an H, so all of this stuff. Reading from this side, I have CHBr and CH2, so they're different. So from this vantage point looking out, these groups are different. Even though they're the same ring, as I read across the molecule, they're different. And here's the thing, if I have a stereocenter, if I have a site, and on the site, I have all of these groups being exactly the same, all of these groups being exactly the same for 100 carbons, but when I get here, I have a D versus a tritium, well then that's still a stereocenter. So you're looking out ad infinitum for any difference. Whether it's at the first point or the 1000th point, it doesn't matter. The groups are then going to be different. So, so this then is a stereocenter. What about here? Well, that's got 2 H's, that's out. 2 H's, that's out. This has a methyl and H, and immediately reading around, I've got CHCl versus CH2. So that's 4 different groups, that's a stereocenter. This has an H, a Cl, a CBr, and a C-methyl. So those are different. That's the stereocenter. Here, same thing. H, Br, CCl, C with that stuff on it. That's the stereocenter. So that molecule has 5 stereocenters. Now, something interesting happens as the number of stereocenters changes. When a molecule has n stereocenters, it can have a maximum of 2 to the n stereoisomers. It will have a maximum of 2 to the n stereoisomers. Take, for example, the compound we were just looking at. This has 1 stereocenter. It will have a maximum of 2 to the n, where n is 1, that's 2 stereoisomers. These are the 2. The one in my left hand, the one in my right hand. So a molecule like this, which has 1, 2, 3, 4, 5 stereocenters, will have a maximum of 2 to the 5 stereoisomers. Now, I'm not saying they're going to have 2 to the 5 enantiomers. That's very different. They'll have 2 to the 5 stereoisomers. And in the next lecture, because we're running out of time with this one, in the next lecture we will pick up and talk about this in some more detail. So the question we're going to ask is, one of the questions we need to ask and answer is when will we expect enantiomerism to arise? Because we saw it arise when the molecule was devoid of a mirror plate. We saw it arise when the molecule was a tetrahedral site with 4 different groups around it. And the question is, which of the 2 features, having tetrahedral atom with 4 different groups, or being devoid of sigma, which of those features is necessary and sufficient for the molecule to exist as a pair of enantiomers? There's a word we want to use here, and the word is chiral, right? And the associated word chirality. Okay? Chirality is the concept of handedness. In other words, although my right hand and my left hand are mirror images of each other, although my right hand and left hand are mirror images of each other, okay? My right foot and my left foot are mirror images of each other. They are not equivalent, because if I have those designer gloves, not the lab gloves, right, which can go in either hand, but if I have designer gloves, my left hand can't fit into the right glove. My left foot can't go into my right shoe. So chirality is the property of a system, a molecule, a body, an object, where they are reflections of each other, they are mirror image of each other that are not superposable. So we can say that my hands have chirality. In other words, my hands are chiral. So these are chiral molecules in the sense that they possess chirality. And the question we need to ask and answer is, what makes me chiral? Is it having 4 different groups around the central atom, central tetrahedral atom, or is it something else?